So I hope it makes sense. So we'll start from very basics, right? And then we'll go through the basic concepts, right? So we are saying like, okay, data structure and its application. First, I will try to give some notions so that later on slides would not be boring for you, all of you. Then I will discuss IoT-enabled cellular 5G and research challenges. And particularly, I will go through with one problem statement today, and we'll see how can we formulate this smart city application problem and then propose heuristic. And heuristic would be based on the concept of graph theory and coloring based model. I hope we all are aware of. If not, still that's okay. I will be covering from basic the advanced version. Then after that, we'll show uh, some performance that we observe from our laboratory, and followed by conclusion and future works. And if time allows, we'll try to discuss another topic as well in between. I hope I'm quite audible, right? And loud and clear.
Yes, sir. Yes, sir.
Yes,
Okay.
sir. Yes, sir.
So please,
Everything is clear and all.
yes, please stay with me because I'm just going to start from very basics, right? But uh, these are pretty important things, right? So those who are from BTech computer science, most probably they are aware of well topic of data structure, but those who are not, just let me introduce for them. So generally we discuss like data structure. So what is data structure? Why I'm discussing this particular topic? Because later on slides, when I will introduce these concepts, I will assume that you know a little bit on this particular topic before going to the mathematics and actual algorithmic part. So data structure is a way data structure is a way of organizing data in a computer so that it can be used effectively. So here I'm just leaving this used term. It is a bigger term actually. Used maybe how can you access the data from the computer? How can you retrieve the data from the computer? How can you insert data inside the database, right? There are a lot of process involved in this particular this word used, right? So if you discretize this particular term DS, so we can end up with linear data structure and non-linear data structure. In linear data structure, generally we come up with static and dynamic. Non-linear, we discuss mainly tree and graph. Static, we all are aware of array. In dynamic, we have linked list, queue, stack. And in today's talk, mainly I will be focusing on graph, that is non-linear data structure and application of graph in smart city scenario. And that particular smart city will be enabling that it is covered by 5G as well as fog computing platform. So let us see how this conjunction is going to make sense in this particular domain. So coming to graph, so I think in simple word, you can say a graph is data structure that consists of set of nodes, or sometimes you can say vertices as well, and a set of edges that are connecting those vertices, right? So we have set of vertices and set of edges, and edges are going to connect with vertices. So here is one example. You can see. I'm so sorry, I'm not feeling very well right now. Okay, so maybe sometimes it may get a little bit disturbance as well. So let's assume there are some set of vertices given labeled with 0, 1, 2, 3, 4, and these lines that you can see connecting these vertices are known as, right? Yes. So I think this makes sense. So here you can see some funny example, actually logical example of friend and not friend. So suppose even in your Facebook, you might have several friends, right? So suppose someone is asking, can you process some relevant outcome out of your friend circle? For example, let's assume someone is saying, can you find out the number of friends that are connected for more than 5 years? So how can we get that particular part? So maybe I can think of, okay, if I am over here, then there are several other friends who are connected with me, and then I can label those friends with the time I am being connected with them, right? Okay, so if there is a friend relation between any two, then there would be an age, right? And each person in the circle will represent a vertex. There are other way as well. You can say like if there are no friends, then we can have no age. So what I'm trying to say, even the real-time scenarios can be converted into graph. Graph is pretty important tool. So let us see how important it could be. So if you talk about application of graph in computer science, we have pretty well-known applications. For example, used to represent network of communications, also used to represent data organization, transform system work or rule-based in memory manipulation of graphs. And graph database ensure transaction safe, persistent storing and queuing of graph structured data. And we also find out the shortest path in road and network. And we all are aware of like we most of the time we use the Google Map where we can see a particular path connecting different cities, right? And that Google Maps most of the time is gives us the best path, maybe in terms of traffic or shortest path or whatever, right? So this is the bigger term computer science where graph application could be applied in electrical engineering. Similarly, we have in design of circuit connections, social science, even graph theory. These are just few examples I am just throwing to you so that you could not get bored why we are going through this particular graph, even starting of the topic, right? In social science, we can say graph theory is also used in sociology. For example, to explore rumor spreading, friendship graph, describing whether two people are known to each other or not, influential graph, collaboration graph. The other domains could be biology, mathematics, physics, and chemistry. So indirectly, you can see none of the domain is free from the graph nowadays. Now, particularly talking about computer network because we need some notion of computer network subject into this talk. So in computer network, the relationship among interconnected computers can be presented with help of graph. Two computers are connected, then there would be an edge between them. Given that those computers are going to represent a vertices, right, in the graph. Graph theory is also used in network security. Particularly, we can use the vertex coloring to find the proper coloring of my 4 colors. How the coloring is coming right now. So graph coloring, I think everyone might be aware of what is graph coloring. Graph coloring is like a phenomenon in which we try to color the graph in such a way that no two adjacent nodes or vertices will have the same color. And the other objective is like we have to minimize the total number of used colors. That is known as chromatic number. Okay. And there is very fantastic application of graph coloring in computer network. So resource allocation in next generation wireless networks. Even we have done a lot of work on this particular topic and published several research papers in well-reputed places as well. So briefly describe the graph coloring. Graph coloring is a procedure of assignment of colors to each vertex of a graph G such that no adjacent vertices get the same color. And we are pretty much sure on the smallest number of required colors. And believe me, it looks like pretty easy, but it is one of the notorious and very difficult problem to solve in general. So here, let's assume we have given a graph and the total number of required color is 3. Let's assume if I am going to color A with some color, then I'm not supposed to color the same. I'm not supposed to put the same color to E and C because both are the adjacent nodes. Similarly, if I'm going to put some color to B, then C, D, E are not supposed to get the same color. So that's the main concept behind this graph coloring. I think this is pretty much clear now. And I request all of you, if you have any doubt, you can ask or you can stop me in between whenever you have a problem. So I'm pretty much free if you are going to ask a question, and I will appreciate it. So okay, so it looks pretty easy that okay, we are going to color one node and just keeping track of its neighboring node and then not assigning the same color to the neighboring nodes, right? But that can be one way to solve the problem. This particular phenomenon will not give us the optimal solution. An optimal solution is NP hard problem. So I'm not going in NP hard problem right now. So let's leave that particular part here. So if in the future, if we are getting opportunity, we'll talk about P hard and P computer parts. But right now, seeing that this particular problem is pretty much hard to solve, then leaving this particular part over here, I'm just going to see some application of graph coloring, making timetable even in colleges or schools, register allocation, operating system you can in computer organization, map coloring, bipartite graph checking, given a graph, if it is bipartite or not. If it is colorable by two colors, then it is bipartite graph. Right? If it is not, then it is not a bipartite graph. Then mobile radio frequency assignment. IoT enables cellular 5G networks that we are going to do. See today's last topic I'm going to discuss. Next part maybe in the future we'll discuss sometime in somewhere else. So today's talk is focused on IoT enabled cellular 5G networks, where we'll see the application of graph coloring to solve a particular. Now saying so, I will stop with this particular graph coloring and data structure, whatever we discussed. Now coming to the another dot. First dot I discussed the graph coloring part. Graph, data structure, that part I was stopping over here. Now I'm going to generate another dot. This dot is known as IoT. And I think this is the second day, so most probably many of you might be aware of IoT and some of you already knew. So in a brief, we can say the IoT is describes physical objects that are embedded with sensor and small processing capacities also has software and other technology that connect and exchange data with other devices and system over the internet or other communication network. Okay. We have several examples you can say. Like nowadays we are connected with IoT, right? Even if you have mobile phone, it means you are connected with IoT. IoT is also a mobile phone. Even if you are using your laptop or you will connect to this particular workshop, sorry, this particular uh, FDP, still you are connected through the IoT device, right? So, in fact, we do not have any particular uh, uh, application where IoT cannot be implanted in upcoming 10 to 12 years, right? 10 to 20 years. Right now, it might look like it's quite difficult to deploy everywhere, but yes, just wait for another 10 to 20 years. We'll have everything connected over internet. Now, the main topic that once we talk about IoT, then IoT come up with three particular components. These are pretty important components. One is computation, communication, and controlling. Controlling you can say sensor actuator. And one more thing, like I want to highlight over here. Most of the time, what happens, people get uh, confused between IoT and sensor, right? So, so both are different. Sensor, we are assuming that it is dumb. It cannot do processing, right? It can just collect data, but processing cannot be done at this point. And it cannot even communicate with the uh, other node situated at a certain uh, meter away. So IoT is a smart sensor, you can say, like which has the controlling power, which can compute some tasks, which can also communicate with the wireless networks. If you just scale it down, we can say like sensing and actuation, maybe you can say data sensing and collection, temperature, humidity, pressure, light, velocity, sound, images. These are coming under controlling power of IoT. Computing, you may be in network processing, fusion, estimation, filtering, aggregation, or finding out appropriate accuracy would also be the other thing. Computation. Communication, if you talk about maybe transmission, reception, like broadcasting, routing, and dissemination. So these are capacity should a particular device have in order to qualify the criteria of different. Now we all are aware of even this FDP is coming with the IoT framework, right? So let us look some basic application where it could be employed, maybe the industry or smart city scenario. So if we just dig around 20 million years ago, we started crawling around. Then around 1784, 1817, 1969, and 2011 onwards, you can see the graph how we upgraded ourselves, right? When we got water stream and mechanical products, then we got electricity, we got IT automation and electronics things, then we have got the robotics. Now we are talking about IoT. Okay? So the next milestone would be Industry 5.0. So there is huge evolution. If we talk about Industry 4.0, we can see, right? We have smart traffic lights, we have smart personal area network, and IoTs are being used in several places such as food, textile, automobile, electronics, factory area, even automating the homes, intelligent transportation systems as well. Now, how this connectivity is coming together, that's important thing we need to keep in mind. These things are coming, and we have industry, then we have technology, and technology is being enabled with internet. Now we are trying to put them together in order to enable accessibility of these industry parts remotely. And so that what we are trying to do, so that we can get a life balance. We can balance life and work. That's what we are trying to do. So that even being at home, we can operate our industry. For example, even being at my home, I can give a lecture, and you can even attend on eve of festival as well, right? So that's what we are saying. Now people are so excited about it. So what's the reason behind this particular theme? Just look the scenario of 2030. The expected revenue out of this market is $14.2 trillion. Right? So almost all the companies are forcing themselves come in this particular framework to make their system smart enough so that it could be enabled with recent technology. So there are different components. If you talk about IoT or IoT, these components may be localization of wireless sensor networks, wireless sensor actuator networks, controlling and managing cyber physical system, industrial big data analytics, virtual sensing and virtual sensor networking, web of things, and for industry. So there are a lot of applications that could be implanted on based on this IoT model. Now coming to the introducing another concept that I didn't do till now is fog. So here you can see the example, right? We are saying, okay, we are going to put things near to the industry and IoT devices will be there. How we are going to connect with these devices? We are saying IoT devices. Still, IoT device cannot broadcast data quite larger distance. If it is going to, because we are saying, okay, we have tiny device that can not be as dumb as sensor, but it will not be as better as supercomputer. Okay, that's what we are saying over here. Now question comes, how can we make it better even? That question is being solved using the fog computing platform. We are saying, okay, let's assume different applications are connected with IoT devices. Then maybe using Wi-Fi, BLE, or 4G or 5G or Wi-Fi. That particular data could be forwarded some local entity where some kind of microscoping can be done. Maybe the data analysis, data computation, accuracy measurement, management of subsystems. So that particular subsystem we are denoting as fog computing platform. It is not as strong as cloud computing, but not weaker as IoT. So it is coming in between the cloud computing and computation of IoT device. So we are saying, okay, we have local computation model which can collect data from IoT devices and further it can compute in order to get the relevant output. If I have smaller content to execute locally, that can be done at fog layer. But if I have bigger things to be done, then I need to push it at the cloud layer. However, there is a problem if devices are directly connected with the cloud, it will charge us the latency. That's the biggest challenge, right? We are not saying like cloud will be just near to us every time, right? Maybe it quite be miles away. Even propagation latency could be quite, transmission time would be quite high. So we are saying, okay, we have a smaller cloud that we are saying fog will be near to us, and that can provide us the local computation of things. Now, if you think of smart healthcare and application of these models, and whatever we are discussing right now is coming under the smart city applications. So here we are saying, okay, we all are witnesses of, right? So even if you are not able to visit hospital, can accurate data be provided to the doctor sitting remotely somewhere, and some computation can be done over there, then suggestion can be, a prescription can be written by the doctor, and the prescription can be forwarded to the respective patient. A relative can give that particular medicine or prescription to the respective patient. The question comes, how can we enable this particular platform? It looks pretty easy, right? It's pretty difficult as well. So we are saying, let's assume a particular person is dealing which can collect EG data, blood pressure, maybe oxygen, other parameters. Then his mobile phone aggregate the data from his sensors, then further forward to the local node, maybe fog computing node, 5G. We do not have 5G, we can assume for 4G right now. Then computation or machine learning approaches could be applied over there. And then based on accuracy or based on feature extraction models, doctor can predict particular disease and then prescribe it. But there are several challenges as well, right? It's not pretty easy to enable this particular technology in current scenario. Challenges are like, how can we prioritize people? Maybe if there is older person, he should be given higher priority compared to if someone is okay. Or a critical person should be given higher priority compared to a normal person. If someone is reaching towards the emergency, then how can we enable all the operations should be ready beforehand? Right? So these are the models. And also we have limited healthcare force work, patient-based services, high-tech services with high touch. So a lot of things needed in our model. I assume, okay, this particular scenario will work this way or that way, but such platform. And in current scenario, we do not have such enough platforms, right? We are approaching for it. But if you just take example, remote surgery, right? So in the current scenario, if we are trying to do, it would be quite difficult for us to do, right? For doctors to do. But it needs microscopic and micro level model just to get the accurate surgery. For those purposes, we need connectivity, infrastructure. Now, if you talk about smart grid and power industry, we have application of models like here the devices, maybe electric vehicles, smart factories, subways and metros, smart homes, smart meters. Everything may send data to the local fog computing node, and this fog computing node we maybe software defined networking or something. Right? Then further it can be forwarded to the cloud center where smart grid can work. There are some other applications as well, maybe smart agriculture, where data could be taken from these agricultural IoT and then forwarded to the some local node, maybe edge or fog node. And computation can be done, and then result could be forwarded to the respective farmer in his or her language. Now, if you talk about smart transportation, right, most of times what we feel, we just Google and we say like, okay, right now there is no traffic, so maybe we can follow this particular route. But after reaching that particular place, we get old. Now it becomes pretty much congested. So question comes, how can we get rid of this particular phenomenon? We can get rid of this particular phenomenon by having a predictive model which can predict us if this is particular scenario right now. So maybe in 1 hour or so, there is this much possibility that there would be crowds. So maybe 4% reaching that particular place may change his or her route. And this could be enabled with help of different fog computing platforms. And then aggregation may be done over cloud and data could be forwarded to the respective users. Like even if you say this waste management even could be enabled with IoT and other things where we can alert and fog computing can the data, and once it is filled, garbage cans are filled, then signal could be thrown to the monitoring person, and then truck can come and then collect the garbage. And right? There are even 1,000 applications, right? But we'll see a few of them, like smart greenhouse gas control, smart water management, mining, food industry, advertisement industry, third party delivery, smart parking, right? Where the concept of fog computing and IoT could be employed. Yes, such platform will need application as well. So for that reason, we need 5G infrastructure. Okay, so if you just see, I will just start with the Jadid Faith. Actually, I'm not follower of him, but still here it makes sense. It says that all things are connected through the force. If you just simply remove the force with the IoT, it is making sense in the current scenario. It's saying like all things are connected through the IoT. Even this particular graph, if you see the number of devices and years, with respect to number of devices and years, we are saying like by 2050, we can have even more than 100 billion devices connected over internet. Question comes, how can we enable them? How can we handle them? Even if we just take the scenario of 2015, right? Maybe we can reach quite large number of connected devices. One solution that comes into picture, like we can evolve around our current scenario. Evolve means if we have 4G right now, we'll go with 5G. It is not just 5G, where different devices such as device-to-device communication, cloud radio access network, cell, multi-radio, cell edge, and densely deployed small cell will be there for service provider, and upon getting the request, they will try to serve the users. And you can say like in the current scenario, people used to say how this would be different from the current scenario. But there would not be much difference, but everything would be densified, right? You can think of scenario of 5 or 10 years back when hardly people had mobile phone. Nowadays, you can see like everyone has almost at least one mobile phone. Right? Well, many people have more than one or two, right? Now coming to this particular problem, we are saying, okay, this will be done. What are the research challenges? Research challenges could be resource discovery, interoperability. Resource discovery, like what? How can we provide the resources? For example, if the IoT device is looking for bandwidth, can we provide the bandwidth? Or if a device is looking for computation power, can we provide the computation power to it? Interoperability. Interoperability means there is two technology existing together or two devices existing together with different technology enabled with them. Maybe one device is working in device-to-device communication mode. Another device is working in just normal Microsoft user. Then how can they interoperate each other? Other part is like we have densified network. How can we make this particular service reliable enough? Reliable means whatever we are going to get will be sufficiently above some threshold value. Then how the latency will play a role? Because we are saying, okay, this would be densified. The latency, okay, more number of users are coming to the picture. How the latency will be reduced? How this communication could be enabled? How the computation could be done? For example, let's assume I have some video to upload. How can I enable the communication or computation? There would be so densified model. Energy, security, fault detection and reconfiguration. These are several research challenges that we need to keep in mind moving toward the next generation in the smart city application. Now, focusing on these challenges, we try to formulate one objective problem. Problem are like how can we jointly formulate task throughput and resource efficiency maximization in presence of task deadline, associativity, interference, heterogeneous resource demands. So those who are not aware of, like here, I'm defining task as the unit that cannot be broken out. Okay, so let's assume if I'm going to just make a call to some of you with my mobile phone, the task is to make a connection between two mobile phones. So we are saying, okay, in overall, I'm trying to maximize the total number of tasks executed. The question comes, we have limited resources as well. Then how can we maximize the efficiency of these resources? Here, particularly, if I'm going to talk about resource, it means I'm discussing physical resource block, that is spectrum available in the network. Saying so, we are also pretty much concerned that each task is coming with a certain deadline. We can not say like if I'm making a call, if this call is not being connected within 30 seconds or 20 seconds, then I start, oh my God, what's going on, right? It used to happen everyone, right? So we are not in the mood of spending much time. So we are saying, okay, task deadline should be bounded. Associativity is there. What is meaning of associativity? We'll see. And we are saying as we are dealing with the 1,000 or more than 10,000 devices at a time, there is a high chance of interference. The meaning of interference we'll see in the subsequent slides as well. And heterogeneous resource demand from each task from tasks. Right? For example, let's assume someone is talking over WhatsApp and someone is just making audio call and someone is making a video call. Required resources or required resources means required bandwidth will differ. Right? So we cannot assume whatever users we have will always need the same number of resources. So we have heterogeneity in some sense. Keeping these objectives in mind, When we look around other existing models, and we found out that by 2019, and I think we were the first, we first published into 2019, saying like we propose a priority-based radio and computation resource provisioning at FAP in IoT-enabled 5G networks. And when just going through few literatures, I'm just adding few literatures over here. If someone is interested, they can get my papers. They can download paper. Even I can provide it later on as well. So, for example, in 2019, Prakul et al. Proposed a matching theory-based pairing model for resource allocation. Here, again, I'm reiterating the same sentence. Resource allocation means spectrum allocation. For fog access point model. Then in 2018, Gu et al. Proposed a joint radio and computation resource allocation in the IoT fog computing model. And in 2018, an optimized resource allocation framework for IoT-enabled fog access radio network by Gu et al. And Wang et al. Have proposed delay-aware resource allocation approach for fog enabling network based on greedy heuristic approach. Keeping all these objectives in the mind, and we wonder that none of available literatures discuss these models altogether in one shot itself that we did in our paper. So coming to the high level contribution of our model, we formulate a task throughput and resource efficiency maximization in presence of priority-based resource demand, deadline, interference constraint, all together as an optimization problem. And we have proven this particular problem as NP-hard. To solve this particular problem in an efficient way, that is not the efficient way, we propose a graph multi-coloring based heuristic. And further, we demonstrated the effectiveness of the proposed heuristic using theoretical, experimental, and test bed and comparing with other existing approaches as well. Here, if you're saying priority-based resource demand, it means if two users are requesting for the limited resources, then whom should we give higher priority? For example, request of resource is coming from ambulance and a request of the resource is coming from a common people. Then ambulance request should be given higher priority compared to ambulance. Sorry, compared to common people, right? Okay, so that's the part. And so these are the contributions that we had made. Now coming to system model, because this is the new theme that we need to contribute, we need to continuously go on. So I just want to, either I should stop over here for 10 minutes or should I continue and stop 20 minutes before or maybe 10 minutes before the 9 o'clock? What's your opinion? Are you there?
Sir, as per your comfort.
I will go then. I will continue, right?
Okay, sir. Not a problem. Sure.
So I think the biggest problem of professor is to start with, right? Once they start, then it's pretty difficult for us to stop.
Yes, sir.
We all are on the same page, right? Okay. Okay. So coming to this, keeping this contribution in the picture, and I hope I'm not boring everyone. So meanwhile, if you have any doubt, please do ask questions. So maybe I can stop over here for a while. If someone has doubt, maybe he or she can ask a question. Anyone has doubt? Maybe we can answer it maybe 5 minutes or so. Still, like bigger term, I didn't show you till now. Bigger term is coming now, the mathematical portion. Till now, what I discussed in last 50 minutes, like some basic concept of data structure. Then I started with graph. Now I had given one example of graph coloring. Then application of graph coloring in several domains, where today I am just discussing IoT-enabled cellular 5G networks, and there are a few more examples as well, few more applications as well. Then I started with IoT, high-level view. I did not go very deeper. Then we saw three components where computation, communication, controlling should be enabled, and several applications either from industry or smart city, then smart healthcare and respect to challenges. Then we started with IoT enabled 5G networks, and we saw several research challenges that we are supposed to follow. And these are really research challenges, and we do not have exact solution till date. Keeping those research challenges into mind, we come up with some set of problems we have taken from these challenges, and there are several more challenges as well. I just tried to figure out few of them. The objectives, we say like, okay, we are just going through with joint task throughput and resource efficiency maximization. In presence of task deadline, associativity, interference, heterogeneous. And few of them, few terms I did not describe yet, but I will be describing with help of example. And we also saw the existing works and contribution that we saw, like we formulated this particular problem mathematically and found out that this particular problem is pretty hard to solve. So we solved this particular problem with an efficient solution using the graph multicoloring model, and we demonstrated the effectiveness of the proposed heuristic. Now coming to the system model. That much I discussed till now. If anyone has problem, you can ask a question. Otherwise, at the end of the lecture, you can also ask a question. Now coming to the system model, we have IoT device over here. And we are saying IoT device cannot broadcast its data to the very far away computing node. It has to have internet connectivity. Setting that we are not connected with Wi-Fi, in most of cases we'll be connected through the base station, mobile tower. Right? Let's assume these IoT devices are sensing some data, and they're requesting to base station that, hey, I have some data. Can you provide me some resources where it can be computed? And that computation can be done at fog access point or fog computing node. The reason it cannot directly send to the fog computing node or fog access point because it is remotely located. It is not directly in proximity of IoT device. That's the main reason. That's the reason we are saying base station is a mediator which is helping out IoT as well as fog access point to communicate with each other. Right? So IoT device will send its task to the base station. It will not directly send a task. It will request task execution to the base station. Then, if I'm saying base station, those who are not aware of, base station simply you can assume mobile tower through which my mobile phone used to get connected. Then base station further forward the resources, make a resource management between FAP and base station. For example, when you are making a call, right, from a mobile phone, first of all, what used to happen? With help of control signals, we get connected, right? If you are aware of 2G, like how the communication is being enabled to ESC, MSC, other things, right? So similarly here we are saying, okay, some control signals is going and their connection is being established. Once connection is being established, then data will be transmitted. Okay. For example, if you once you are going to call your friend, then there will be a ringing on your friend's side. Then he will pick the call, and you both can communicate with each other, right? Like it's two-way handshaking, right? Same thing is happening over here. So after that, what will happen? Okay, one more, some parts I need to describe over here. One is known as ERB. Till now, I just given a bigger term that this is resource. But from now onwards, we are saying if I'm saying resource, it means it is physical resource block. So what is physical resource block? Physical resource block or PRB is the smallest unit of radio resource, which actually consists of 0.5 millisecond and 180 kilohertz in bandwidth and it helps out to connect IoT and fog access point or connect any two nodes, two devices as well. Physical layer, if you go ahead, you can find out narrowband IoT carrier where we have PRB and total number of PRB could be could be 100 at 20 megahertz, and similarly it varies 1.4 to 20 megahertz. But given that, I'm just going to define one slot that a PRB contains 0.5 millisecond. A pair of PRB is supposed to be allocated for transmission of tasks from IoT to the fog access point. Without this, I'm saying like this particular data will not be transmitted across this network. Okay. So I hope this PRB is making sense now. If you're not making sense, still you can assume there is a block which can carry data. And block consists of 0.5 millisecond in time domain and 180 kilohertz in the frequency domain. That's all. Other elaboration, there are, even if I just go PRB, it will take even more than 1 hour or 2 hours just to describe PRB. But this is the particular part that we need to understand, whatever we are going to discuss in the subsequent slides. Further details you can always get from my research papers, right? Okay, so this much is done. Now let's go ahead. Now we talk about different applications. Let's assume I'm just discuss surveillance camera or real-time gaming or conventional videos. So in surveillance camera, if deadline is, let's assume a camera is capturing the video, sending it to maybe some remotely located computer where it is being displayed. Let's assume a hypothetical assumption. The data size that is being transmitted from that particular camera to the remotely located server is varying between 128 KB to 348 KB. And deadline is bounded between 100 to 400. Let's assume it is taking picture and just sending it, right? Or if it is taking video, it is very lower quality. That particular scenario, what will happen? Quad number of PRBs will vary from 5 to 30. Similarly, in real-time gaming, if deadline is bounded between 50 to 300, and required data that you are accessing to play the game is varying from 64 to 512, the number of required PRBs may vary from 3 to 70. Similarly, suppose you are just uploading a conventional video to YouTube channel. You are making reels or something, right? It's quite famous nowadays. And you're saying like, I want a particular deadline to be bounded for my reels, right? Maybe I cannot go beyond 1 or maybe 1000 milliseconds. It is taking, my mobile phone is taking more than 1000 milliseconds just to upload a simple video. Now it's network is not good enough, right? And saying so, we are also saying like data size, whatever data video we are uploading, maybe very small size, 64 to 600 KB. The required number of resources or PRB will vary from 3 to 19. That's no sure. So why I'm discussing all these numbers? I'm discussing these numbers so that you can be familiar that the kind of application we are going to deal with this particular network is not uniform. Maybe someone is using for surveillance camera, someone is using it for real-time gaming, someone is using for conventional uploading conventional video or downloading conventional videos. Okay? So the required number of PRBs will just keep on varying. That's giving us a heterogeneity of the required resources. Now, coming to this one, if task being transferred from IoT to base station, maybe I can. This could happen. Task will be transferred from, after connection, task will be transferred from IoT to base station. The base station will forward the request to the fog access point or fog computing node, then computation will be done over there. The result will be responded back to the base station, and base station will forward result to the respective IoT device. In this particular process, there will be several kind of latencies involved, but particularly I am discussing just three. One is transmission latency, execution latency, and response latency. Transmission latency, like how data is being transmitted from IoT to access point. Second one is execution latency. That execution latency will involve at fog access point. How much time the fog access point is taking just to execute the task. Response latency is like sending request, sending response from IoT device across the base station. Now I'm going to quickly derive all these parts. Let us see. I hope you are okay with mathematics. If not, it is simple math. What we are saying, any task, if you see where we are going, any task will only be computed if IoT, base station, and fog access point, all three are coming together. Why base station? Because PRB value will be provided from the base station. We should come together to a task. That's what we are going to do over here. So we are saying, okay, we will play between IoT device, access point, and PRB. And set of these entities are denoted as capital I, capital I, and PR. Capital I represent IoT device, F represent FAP, and PR represent PRB. And out of them, particular IoT device is represented. Let's assume I am saying II. Particular FAP, let's assume general any normal FAP key will be denoted as FK, and a PRB is just N. So we are saying a binary variable YKIN is equivalent to if the NF PRB is assigned to IIFK. Okay. And who is going to assign this one? This will be assigned by the base station. Otherwise, this value will become 0. What we are saying, in order to offload a task or in order to complete a task, YKIN value should be 1. This task cannot be. Okay. Now we're saying, okay, in elaboration to this one, we are saying IoT and FAP will match SKI, IKI becomes 1 if this is non-value, this value is non-zero. We are saying otherwise it will not match, and we are giving the smaller value, that is minus infinity. Now main objective is to come up with the task throughput. So the way I have defined, or we have defined a task throughput, nothing but this summation value. This how many tasks is being computed, and the task is saying the number of ones present in this particular binary variable. And how is it going to happen? This will be happening across K, I, and N. K is fog access point, I is IoT device, N is resource. And we are trying to maximize this particular value. Okay, that's what we are trying to say. I hope this makes sense, right? Please stay with me, otherwise from now it could be a little bit difficult for you whatever I'm going to discuss in subsequent slides. Okay. Now my main objective is to maximize the task throughput, which is subject to task latency. Latency, we are saying deadline constraint, right? And in this particular deadline, I am considering transmission latency, execution latency, and response latency. Transmission latency is considered as alpha YKI, execution beta YKI, response gamma YKI. and everything should be less than some predetermined threshold. Here are some assumptions that we are making in our model. Our model is not perfect, right? So some assumptions we are saying, like associativity assumption is like task can be offloaded to a single FAP at a time. Cannot be offloaded to more than one FAP. The other concept like interference. Any two neighboring FAP can create interference to each other's serving IoT. This interference may degrade the signal strength. And an IoT can demand the high number of PRBs based on what kind of application it is dealing with. So these are assumptions that, based on these assumptions, I'm going to formulate the problem. Now, here is the formulated problem, that is optimization problem. We're saying, okay, we are trying to maximize the task throughput subject to lines, associativity, interference, priority. First one is saying the deadline of task is bounded by tau I value. And second one is saying like associativity, like one IoT device can offload its task to be at a time. Third one is saying like one PRB can, only one PRB can be assigned to the interfering system. And high priority tasks should get the required number of tasks can get less number of PRB, whatever it is demanded. Okay. And this is not pretty easy problem to solve. It is NP hard problem to solve. We have proven it in our papers. But I'm not just going to describe all those things. Okay. If someone is interested, maybe they can look the paper. This is optimization problem. It's a pretty difficult problem to solve. So in order to solve this particular problem, I'm going to discuss a heuristic. Heuristic is based on 3 different phases. Anyone has problem in optimization? How is it coming? So the rest of the topic that I'm going to cover is just simple solution this particular problem that we just see over here. This particular problem is an optimization problem which we need to solve. So we are proposing a heuristic for it. And this heuristic is based on 3 phases. Phase 1, we are saying minimum resource requirement. The second one, we are creating interference graph transformation. Phase 3, we are saying the resource allocation. Now, whatever I discussed in the first 5 to 10 minutes will be used over here. Graph coloring, graph things, right? That's the reason I started with. So we are saying, okay, here you can see we are saying the VI number of PRB could be asked by each task generator or devices. And we also saw one example here, like how this DI varies. So we are saying, okay, we have high priority, low priority tasks, then how can we deal with them? So let us go with first one, minimum resource requirement. Let's assume we have given 5 power access point A, B, C, D, E, and 7 resources. Resources are denoted with different colors. Resources means PRBs. A, B, C, D, E, F, G. And minimum required resources are 2, 1, 1, 2, 1, and maximum quotas are given 3, 2, 2, 2, 3, 3. Okay, so if I'm saying 2, it means minimum requirement is 2, means FAP A is dealing with a task which need 2 PRB. If it is saying 3, A is looking for 3, it means it needs 2, but its demand is 3, because one PRB is extra is being asked because It is dealing with the low priority task as well. We just need one PRB. Okay. So if you are just going to fulfill even the minimum requirement, so if you just sum up to 1, 1 to 1, we'll end up with the 7 values. And here you can see we have just 7 available PRB. So minimum requirement we can fulfill about the secondary users, or how can we fulfill the maximum quota? I think this is making sense to you, minimum requirement and maximum quota. Let us go ahead with the deployment of FAP. Let's assume we have this deployment scenario A, B, C, D. And we are saying any two FAP sharing the common region, then there is possibility of interference. So there is possibility of interference between A and B, A and C, B, A, C, A, B, C, and E. Based on this one, we are representing this particular topology where vertex is denoted by the FAP and edge will be denoted if any two FAPs sharing the common region. Right? So let us go ahead. Based on this assumption, here you can see A, B, C are part of complete graph, and B is connected with D because they are sharing the common region, and C is connected with E because they are also sharing the common region. Now we get a graph, and this particular graph is known as reference graph. Right? Now I'm just going to label the minimum requirement and the maximum quota at each. For example, let's see the minimum requirement of node B is 1 and maximum that is asking for 2. Right? Similarly for A, C, D. Now our main objective is to find out the minimum requirement or fulfill the minimum requirement first of all. Then if we have available resources, then we can go ahead with the fulfilling the maximum quota. Okay, so how can we do it? So I'm just going to split this particular graph in another graph that is known as derived interference. How this splitting is being done, shown over here. We are going to split each node in such a way that it is equivalent to number of its required PRB. Give me just 1 second. Okay, for example, here you can say A is being split in A and A dash. The reason is that it is asking for 2 PRB. B is not split in any other nodes because it is just 1. C is same, E is also same, but D is also asking for 2. So D has been split in D and D dash. Okay. Now question comes, how can we solve this particular problem of minimum requirement? So we can solve this minimum requirement problem putting or labeling this particular derived graph with graph calling approach. In graph calling approach, one thing we need to keep in mind, MIS. So what is MIS? I need to explain. MIS is independent set that is not a subset of any other independent set. So question comes, what is independent set? So independent set is set of vertices which are not sharing any common edge. For example, B and E are independent set because they are not neighboring nodes. They are not sharing any common edge. Similarly, A and E, but A and A dash are not independent set. Now, I'm just going to apply the MIS. I think MIS term is clear now. So let's move ahead. Let's assume I'm just going to find MIS. First MIS is coming like ADE, then giving the lowest available PIV. A is getting A, B is getting A, E is getting A. Why they are getting the same one? Because they are independent set, right? Not just independent set, they are also maximal independent set. We cannot add any node in this particular set so that it can have suitability of independent set, right? We get first independent set as in set ADB, ADE and colored with the A. Yeah. Now I am going to find out the next independent set, maximal independent set, that is A dash and D dash. As A is already being used, so I'm just giving the next available PRV, that is B. Then I'm finding another one, C, that is B, and labeling is C. And C is labeled with D. So total we have 4 independent sets. Here you can see the significance of coloring problem. Initially we started required as 7, but using this coloring approach, they are able to solve using just 4 PRVs, not even 7. So the remaining PRVs could be utilized for serving the more priority tasks. Right? Okay, so this much I think makes sense. And here is the pseudocode. Whatever I just shown you, given or written in the pseudocode format. This is simple algorithm, and this algorithm you can also download from my paper as well. I'm not just going to explain each and every step. So high level I can say we have interference graph, we have a minimum requirement of PRV for each node, and then PRV set and an empty set L equal to 5. Then we are saying number of PRV are for the maximum quota. Okay, so what we are doing, we are just creating a click of size, the required number of PRVs, and each node of click DV mean inherits all the edges of vertex in the new extended interference graph. And while V dash is not empty, what we are doing, we are picking the MIS, resizing the lowest index PRV, and then just labeling it, keeping the set L. We just keep on going for all vertices until either it is being labeled or number of PRVs is empty, right? At the end, we can find out R equal to PRV means the remaining number of PRV that can be utilized for the maximum quota. The maximum quota of the tasks. This is phase 1. By this one, we just get to know. For example, 3 PRV can be utilized maximum quota of this particular. Now coming to second phase. Interference graph transformation. So what we are doing over here, we are saying each FAP is going to be split or divided into 2 dummy FAP. Why we are doing so? We are doing so because we are saying each vertex, that is each FAP, is dealing with 2 kinds of services or tasks. One is high priority and the other is lower priority. High priority we are trying to represent with history FAP, and lower priority is the elaborated. Same. We split each node into vertices and then connect them each other. So we create a click of size 2 every time, and also borrowed the previous edges originally collected in the original or previous graph. For example, if you take connection between B and D, right? we labeled B with BS and BE. Where BS denotes steady FUP, B denotes elaborated FUP. We also split D into two dummy nodes, that is DS and DE. Then we created a click of size click between DS and DE. Also, all the nodes B and DS and BE as well. Also, all the nodes BS, BE are also each other. Why is it coming? Because B and D both were connected in initial car. Okay, that's what is happening. Similarly, for the other pieces, and this is the pseudocode. This is pretty easy pseudocode. Here you can see like what we are doing. So whatever I did just discuss over here is given in the pseudocode. So I'm not just going to explain it. It is pretty straightforward. Now coming to the third phase. Once we get the derived interference graph, derived instance, each node is split into the two vertices labeled with AS and AE. Then actual resource allocation will be done over here. But how we are going to do? We are going to do that part using the maximum weighted independent set, that is MWIS. And we are doing so in such a way that interference, the whole outcome should be interference free. Like we are not supposed to use the same resource in the neighboring nodes. This is similar to the graph coloring problem. And finally, we are seeing allocation satisfy the minimum requirement of FF. We do not claim for the maximum quota. Maybe we are not, but in most of the cases we are seeing like it will fulfill the minimum requirement of given that we have sufficient number of Okay, so maximum weighted independent set. Earlier we saw the weighted maximal independent set. Now we are saying maximum weighted independent set. The major difference is like here we are giving the higher weight the node labeled with S compared to the node labeled with E. So just finding the applying the same procedure whatever we did earlier. So here VA will be assigned to ES, DS, ES, B will be assigned to DS, C will be assigned to BS, CS will get D. 4 are done. Now remaining 3 we are going to utilize in such a way that it can be reused throughout the maximum number of times it can be reused. So same process we can follow for the remaining 3 colors or 3 PRBs, and this is the final outcome. And here we can see it will fulfill the requirements. And here is the main resource allocation algorithm. So we have transformed interference graph with maximum quota at each node, and output is giving set of PRB to each node, right? That's what we are seeing over here. Okay, so we are just iterating while B is not empty to for each PRB. Select the maximal weighted independent set from the set of vertices, and then assign and make that particular, if demand of that particular node is not empty, means it also needs more, then assign the PRBN and update the demand. It means demand should go down. Else, we are saying like, okay, if it is not the scenario, then temporarily we are assigning the PRB to the. So, pseudocode is pretty easy, so you can follow it. Now coming to, so we discussed till now the all 3 phases. Now coming to the analysis part. We found out the computation complexity of order of n k squared rho N is number of resources, K is number of FAPs, and rho is time complexity for finding maximal weighted independent set in a graph, which is actually NP hard, but we have given approximated solution for it. And lemma we also proven, like if propagation, we are saying if propagation latency of IoT devices carrying 504 bits of data is bounded by 0.5 milliseconds, then our proposed heuristic bounds over the required number of PRBs as this equation. And it is derived as H is the high priority task, L is low priority task, Q is peak size of the graph, delta is degree of the interference. There are a few more analyses given in the paper, so but I'm not going into so much details. I'm leaving that part to you. Now coming to the performance study. So what I discussed till now I discussed problem formulation, solution, and some analysis of the proposed solution. Now I'm going to show you the experimental analysis of we are saying determine utility, and everything is done on MATLAB first of all. So we are saying like utility-based resource allocation as a surrogate of task suppose that we exploited in our model. There are some parameters that we have taken based on the other reference paper. Accordingly, we have created our simulator. Utility defined as this ratio, number of assigned PRVs to the required number of PRVs. Now let's move ahead. And here you can see we have we plot this particular graph, which is showing a relation between interference edge density to utility percentage, saying that as the interference graph or edge density increases, utility of the system goes down. Those who are not aware of interference edge density term, it is nothing ratio between actual number of edges present in particular graph to the total possible number of edges in the graph. Total possible number of edges could be NC2 in a complete graph. Reason behind this model is like increase in interference. PRB. That's the main reason. Now coming to the impact of PRB or utility, number of PRB increases, the utility percentage also increases because more and more number of tasks can be executed now. Also, other observation you can see as the number of IoT devices increases, utility also goes down relatively. Okay. And average PRB efficiency is measured from FAPs and average PRB efficiency with several demand set. Number of FPs we consider 10, 20, 30, 40, 100. And average PRB efficiency with increasing or varying number of demands plotted the outcome. So here you can see as the demand higher, so we have good chance of maximizing the average PRB efficiency. Average PRB efficiency is defined in such a way that how many number of times we are able to reuse the same PRB in our lecture. Okay. So that's one model. And as demand increases, we say like, okay, overall demand increases, but the usability also increases in the similar fashion. Those are few results that I just discussed. Many more are given in the research papers that we have published. Now coming to prototype implementation of this particular model. What we did over here, we created a lab-based prototype model where we have laptop, mobile phone, Raspberry Pi. So this mobile phone, a laptop, and one Raspberry Pi are considered as IoT devices. And another Raspberry Pi act as power access point. and everything was connected over 4G network. Okay, and we are transmitting several tasks from these IoT devices for computation and Raspberry Pi and seeing the output. And here we compared our model and we found out that once the data size increases, total latency increases. And we also observed that there is slight variation between experimental and type results. The reason was pretty much valid that we assumed 5G infrastructure, we are using the concept of 4G mobile phone. That this particular setup developed over 4G. Simulation result is giving the 5G model. So our model somehow comparable but better as well. So we also compared with other existing approaches to other models, and we found that it is giving us 35 to 40% improvement over the existing approaches. The reason was why we get this particular improvement is like using the concept of graph coloring and the reusability of the resource. That's the main reason. And we also implemented the whole architecture over real-time, real-world data analysis. This data set was taken from Australia and Melbourne City, where you can see we have different dots. One is FAP, another is IoT. Right? FAP is denoted in shaded blue color and IoT is denoted in red color. And total coverage area was considered 500 meters, and 125 IoT devices and 94 FAPs were considered. Latitude or longitude you can see here, right? So based on this one, once we tried to do our experiment and we compared or on the total number of available PRBs from 10 to 100, task throughput was quite good enough with respect to IoT demand. So what we get till now that whatever we discuss is not just prototype or experimental results, it also give an efficient solution for the real world data as well. Now, as we have time, so I also this is the particular paper that I wanted this particular talk I wanted to discuss about this model. So there are a few more works. If time will allow, maybe not today, maybe next or some other lectures I will discuss on these particular topics. Some other works that we are currently focusing on, like joint data rate and resource efficiency maximization in D2D IoT enable smart city applications in the domain of 6G. And also some of my PhD scholars are working in the domain of smart healthcare resolution, like how can we can monitor the patients and a quick decision can be taken based on different scenarios. Some ongoing works like use of machine learning UAV in the domain of healthcare, where we are thinking to apply the federated learning concept between base station and UAV, and data may be transmitted from patient to the UAV. And then computation can be done between UAV and base station. In overall process, we are saying there is a model owner which would like to maximize his revenue. So the overall model is like revenue maximization via stable matching and graph coloring based resource allocation in UAV assisted WM. And this work is we are going to submit in few days and review. And there's a prototype for this setup as well. And we have found out a result that is comparable good enough for the UAV and smart healthcare, and everything was done over this setup was done on 4G. But experimental results or simulation results were obtained on the 5G. Yes. Now the other works are like this is also under review, got first revision, where we are saying like how can a patient be treated even on board ambulance. So we formulated this particular problem as NP hard. I propose solution as well. I'm not. I don't think we are going to discuss it now. So we saw like, okay, loss aware for data learning for service migration in multimodal e-health services. And everything was done over the 5G scenarios. There were different RSUs. RSUs were connected with each other. And then this was connected through the hospital for the hospital doing some computation and then providing data to the doctors, and then doctors were giving recommendation even patient is going through the in the ambulances. Okay, now if I going to conclude my talk, so in conclusion and future works, I just discussed the basics of some concept behind data structure. Then we come up with the IoT enabled fog computing platform. We further propose a, a graph multi-coloring based resource allocation algorithm to solve it and demonstrated the effect of different parameters over the utility and latency through experimental result, prototype, implementation, and comparing with the existing works. There are 1,000 works on top of it. You can few of them are given over here. Maybe I can just discuss with you, like dynamic network model with varying traffic rate with non-uniform computation capability, enable FAP. Other could be like load balancing at FAP. The distributed algorithm, we can think of error prediction and alarming. And we can also think of several other applications, as we discussed here, right? With the concept of smart healthcare, this particular framework. Other could be the concept of UAB, evolving UAB, when the whole networking model itself is pretty dynamic. How can you enable the resources part? How can you compute the resources efficiently? Because whatever I discuss, assuming that IoT device is not mobile, or FAP is just fixed at particular point, base station is fixed at particular point. What if my computation device itself is mobile? And these from the source where you're collecting the data is itself mobile. Then how things are going to happen? That we already solved this particular, but as this work is under review, so I cannot reveal more. And here as well, like the other applications, how can we minimize interference from different MUEs, different kind of access point, different kind of IoT devices. And by the way, this work has been published here, so you can track that code. So those who are looking to read my contents, whatever I discussed, most of contents I discussed from fifth reference, you can see, like on maximizing task throughput in IoT enabled 5G networks and latency and bandwidth constraint. And this particular paper has been selected as a best paper candidate award paper in USA, Washington, my postdoctoral tenure over there, 2019. An extended version of this one you can get in reference 4, where we got this one. And if you are looking for application of 5G, trying to solve with respect to, and by the way, let me just go through with a few papers where the graph theory concept has been applied. So reference 4, 5, reference means my published paper, and 8. There we have applied the concept of graph theory and coloring, either solving the resource allocation problem or some other allocation problem, but everything was under umbrella of 5G. Recently, I have published one paper where talk about cyclic stable matching inspired resource provisioning for IoT-enabled 5G networks, and it got accepted in IEEE transition of vehicular technology, where we said, okay, let's assume we have three entities. One is IoT device, another is some local station, another is a fog server. If they form a cycle somehow, then how can we solve this particular problem? This problem becomes even more challenging then. So this problem has been solved even, it has been published as well. And the recent application of remote health monitoring 5G based on criticality and utility over the concept of fog computing model we have published in IEEE transactional service computing. And if some of you are aware of, you can download and read this particular paper. If you're not able to download, just drop me an email. And third one, what we did, we tried to apply the stable matching based concept for providing the or maximizing the service providers revenue under umbrella of 5G. And we use the concept of stable matching. Fourth and fifth, I just discussed. I have just discussed the smaller one, the fifth one. Fourth is a extended version of the fifth one. You can just download and get it through. The sixth one is another concept of maximizing fairness for resource allocation in heterogeneous 5G networks. That was also published in IEEE TMC 2019. These are few highlighted topics related to 5G, and the application may be the smart healthcare or smart city, and that has been already published. If some of you are looking, you can just go through or Google my profile and get those papers. If you're interested, you can even collaborate with me. Now I'm open for questions. Thank you so much for your patience. I hope you are awakened now. Over to you.
Thank you so much, sir. Participants are allowed to ask questions.
I am not able to return on this one. Is there any question?
Now the house is open for asking questions. Participants, please. Anyone?
I think it was a very lengthy and informative discussion. Thank you, Dr. Ajay. And if we agree, we can take a 10 to 15-minute break. We can rejoin.
Or
we want to
what are we
continue?
supposed to do after 10 to 15 minutes?
If the candidates have some queries, then we can answer them.
Okay. If possible, can't we some of it right now? If it is necessary, then obviously we can
Yes,
go.
we can continue with the discussion if it is comfortable to you. It was only for you, sir.
No,
And you are talking continuously since last 2 hours.
No, that's okay. Please carry on. I think we can save time, right?
Yes, sir. We can continue with the discussion. Yes, any of the participants, please feel free to discuss anything with the sir.
Even you can send your message over chat. I can read it out.
Yes, any query? If any query, you can type it in the chat box.
Query or constructive feedback is also pretty important for me. I hope I bored them enough.
No, the discussion was very informative. The people from non-computing background may be
That's why I started with the basic of data structure, right?
Yes, yes. It
Yes,
was started
yes.
with the basic of data structure from the graph theory,
Yes, yes.
then applications. The flow of the talk was very good from the basic to the advanced.
Keeping in mind that the participants are from versatile backgrounds. So if there is no question from any participant, then thank you very much, sir, for such a subjective and informative talk. My gratitude to you for accepting our invitation on such a short notice. I truly appreciate you and your time you spent for us to be on this FDP in the online mode. Participants got a lot of information and inspiration from you as you have done a wonderful job at this age. The way you have explained the system model was very impressive as the participants are from diverse backgrounds and you have done a justice to the talk. Over to you, Sudeep sir.
Thank you, Kavita. I also appreciate the efforts of Dr. Ajay Pratap Singh that he accepted our invitation on such a short notice, and he prepared such a magnificent and wonderful talk for our participants. I hope that all the participants have enjoyed the talk and they will really explore some of the ideas and apply some of the concepts shared by Dr. Ajay Pratap in their research work. Thank you everyone for being such a patient listener.
And also, I would like to thank you all your team actually working on this occasion of Holi as well. Right?
Yeah.
It's really very.
Actually, March was the last month to conclude this. It was already postponed by 2 weeks due to the NAC